Right now, we have two equations. They are and the vector C was C at R equal to now the operator is in non-primed coordinate, so we can take the operators outside of the integrals. At the same time, we are interested to write the vector field C as the gradient of a scalar function and the curl of a vector fields. So we are going to take the gradient and the curl operator outside of the integrals for our convenience. The next thing I need to do is incorporate these two equations into the integrals. So let's see what we get. Let's rearrange the terms. Now the expression for C was, now the first truth term will be similar. In third term, we can apply the divergence theorem. So it would be ds prime dot C at r prime by r minus plus minus 1 by 4 pi curl of ds cross C at r prime by r minus r prime. So we had a condition in this theorem, which is, so these two integrals have to converge. In this situation, dimensional analysis helps. So let C is a function of order of r to the power a. Divergence theorem says so the right side of equation is order of r to the power a plus 2 as ds equal to r square sine theta d theta d phi. Then if we say on right side, divergence of C finitesimal volume, ds will be in order of power r to the power cube. So from here we can say divergence of C is at order of r to the power a minus 1. So if we want to get the order of omega for divergence of C, r to the power a minus 1 divided by r minus r prime, which is in order of minus 1. Then there is an infinitesimal volume which is in order of 3. So it is r to the power a plus 1 in order of. The condition is omega should converge all over the space. So a plus 1 should be less than 0. So a should be less than minus 1. So we can consider that C is in order of r to the power minus 1 plus epsilon, here epsilon greater than 0. So if omega converges all over a space, C has to go to faster than R inverse. Now in third and fourth integral, so we have to evaluate this quantity at surface. So it goes in order of r to the power minus 1 minus epsilon, then minus 1. So at order of